Hi all, let's do some 5-minute physics on alpha, beta and gamma radiations. In particular, what I'm going to go through is how we describe the nuclear transformations that take place when alpha, beta, gamma occur. I'm assuming that everybody has done alpha, beta, gamma at GCSE and is at least somewhat familiar with what they are and their properties. So I'm going to focus on the notation and how we write those decays. The notation that we use is standard, and it looks like this, where X is the chemical symbol of the element that's involved, A is the atomic mass, and Z is the atomic number. So what do those mean? A, the atomic mass, tells me the number of nucleons in the nucleus for the given isotope that we're dealing with. The atomic number, meanwhile, tells me just the number of protons. So A is the combined number of protons and neutrons, while Z is just the number of protons. So an example would be uranium-238. It has chemical symbol U. Its mass is 238. Its number is 92. What that tells me is that there are 92 protons in the nucleus of this isotope. The rest of this mass comes from neutrons, so therefore there are 146 neutrons. So if you look on a periodic table for uranium or any other element, you'll frequently see that the atomic mass is not an integer, and that is because periodic tables frequently show you uranium and they include all of the different isotopes, so the atomic mass given is a mean, it's an average of all the different isotopes. When we're describing nuclear transformations, it's typically a single isotope that we're talking about, so that atomic mass will just tell us the total number of nucleons, the total number of protons, plus neutrons. These are nucleons, they live in the nucleus. Okay, so let's have a think then about alpha, beta, gamma. Alpha, as hopefully you're all aware, is 2 neutrons, 2 protons. It is a helium nucleus, therefore it has an atomic mass of 4 and an atomic number of 2. We would describe then an alpha decay like this. If I use uranium-238 as my example, if it undergoes alpha decay, it turns into a new element that I'll call X in the meantime, plus the alpha. The atomic number and the atomic masses have to balance. So I know that this new element has an atomic mass of 234 and an atomic number of 90. Then I can go to the periodic table. I can look up element number 90, and I find that that's thorium. So I can fill that in. And yeah, so everything balances. This is a pretty straightforward process, really. We just need to make sure our atomic masses balance and our atomic numbers balance. Beta is marginally more complex. We write beta like this, and there's a reason for that. A beta particle is a fast electron. There are no electrons in the nucleus, none that live there, so it comes from, if you think back to your particle physics, it comes from a flavor change in a down quark, in a neutron, that's a neutron, becoming an up quark, therefore a proton. A neutron has a charge of 0, a proton has a charge of +1. We obviously need to balance charge. There's a flavor change here, so this is a weak interaction. So there's going to be a neutrino involved. Neutrinos have 0 charge. So to balance lepton number and to balance charge, what we need to add in here is an electron and an antineutrino. So during beta decay, this is the process that takes place. Because we haven't changed the number of nucleons in the nucleus, we've turned a neutron into a proton. So the total number of nucleons, neutrons, and protons combined stays the same. We have, however, increased the atomic number of the element that has emitted the beta particle by 1. So that's why we write beta in this way, so that we can balance our equations. I'll show you an example. If I take carbon-14, carbon atomic number 6 has 6 protons. Carbon-14 has 8 neutrons, therefore. Carbon comes in a handful of different isotopes. This is actually the isotope used for carbon dating. When this undergoes beta decay, I create a new element X. I add in my beta. If I have 0 and 1, sorry, that is a 0, not 6. If I have 0 and 1, I can just balance my top line, my atomic mass, and I know that my new element has an atomic mass of 14. I balance my atomic number. 7 minus 1 gives me 6. I go to my periodic table, I look up element number 7, I find that that is nitrogen, and I'm job done. So that is the notation we use for beta. When we're just dealing with the nuclear transformation in radiation, we generally don't or are not obliged to write the antineutrino in. If you're writing this type of particle equation, you absolutely must include that antineutrino to balance your lepton numbers. Finally, we're left with gamma. Gamma is the simplest of all. 0, 0. Gamma doesn't alter the structure of the nucleus. What happens with gamma, if I go back to my uranium example, after the alpha decay, there's energy released with that. The thorium nucleus that's left behind is excited, has got a whole bunch of energy, and it can be immediately or it can be an extended time after that alpha decay. But what will happen is that that thorium will simply emit an alpha particle without, will emit a gamma photon without undergoing any structural change. It is worth noting that the half-life for the gamma decay after the alpha decay is not necessarily in any way linked to the half-life of the alpha. So this might be a fast process, it might happen, as I say, almost instantly, or it might be quite a long time afterwards. But gamma is the simplest in terms of it doesn't create any changes to the structure of that nucleus. Yeah, so that's it.